Always, sometimes, never. Now we want to look at whether two vectors in Rn, in other words, two vectors of length n, if we look at the dot product, if x transpose times y, or the dot product of x with y, is equal to the dot product of y with x. In other words, we're asking, is it true that the dot product is commutative? And the answer is yes, it is. This is always true. How do I know? Because I can prove it. And how do we prove it? As usual, we start with letting x and y be arbitrary elements in Rn, in other words, arbitrary vectors. And we look at one of the sides of the equation, say x transpose y. Well, we know the dot product, that is x transpose y, is a scalar that we could find by adding the product of the entries in x, the chi i's, to the corresponding values, components in y, the psi i's, and adding them I from 0 to n minus 1, because that's the definition of the dot product. But we know that multiplication is commutative, and these are just numbers, scalars. And so this is equivalent to the sum I from 0 to n minus 1 of psi I times chi I. Because multiplication is commutative on reals. But this, by definition, is just the dot product of y with x. So clearly, dot product is commutative. Now, actually, how did I know this is my proof? What I did was I started with the definition of dot product for the left-hand side. And actually, in my mind, I looked at the definition of dot product for the right-hand side. And then I noticed that these two were equal by multiplication being commutative on reals. So actually, although I wrote the proof starting from one side and ending on the other side of the equation, in my mind, or if you're not quite so experienced with this, you could do it on paper. You could start with each one of the sides of the equation and notice that they are equivalent to one another or equal to one another at a certain step, and then write out your proof. So that's the strategy. In our case now, we've proven that the dot product is commutative.